Hello everyone and welcome back to another video. Today I wanted to put together the first entry in my series on number theory. And I was really impressed by the performance and subscribership gain to my relatively small channel from my Introduction to Proof Techniques video, so I'm really excited to start getting into number theory and go through this series now. And for those of you just subscribing, I release math videos once or twice, maybe twice a month, depending on how this series performs. All the other content is philosophy. So if you're subscribed for one or the other, just know that the other content is probably coming next week, or I'll try to do once or twice a month for each. So without further ado, let's jump into number theory. And to begin, what is number theory? In simplest terms, number theory is the study of natural numbers. It's also the study of integers, and most of what we're going to talk about in this video, particular videos, is the integers. But in general, the most definitions that I see refer to number theory as the study of natural numbers. So what are natural numbers? If you remember from my Introduction to Proof series, natural numbers we denote by this symbol, and it refers to the positive whole integers. So the counting numbers like 1, 2, 3, 4, 5, 6, etc., all the way to infinity. Ooh, that is a awful bracket. Let me redraw that quick. That's a little bit better. And these numbers are, and sometimes people include 0. The book that I'm using, and typically what I've seen, people don't use 0 in the classes I've been in, but sometimes people will include 0 in the natural numbers. And they're called natural numbers because they naturally arise from a human need to count individual discrete objects. So like on my desk, I can see I have 2 pens here, or I can see I have 2 mouses, one for each of my computers. I have 1 microphone, I have 1 webcam, things like that. So in our everyday life, we have this need to count individual numbers. We notice a need to count different things in our day-to-day life. So these are called natural numbers because they arise from a natural need to count discrete objects. For example, I have 5 fingers. That's probably the first one that we use when we're counting. We use our fingers. And as a result, we use these numbers every day. So I think their usefulness is fairly obvious to most of us. And as a result, I think number theory is the best place to start as a journey into higher level mathematics, because all of us are intimately and intuitively familiar with the subject that we are studying, namely the natural numbers, the counting numbers. We count every day. We see these numbers and patterns about them on a small scale in our everyday lives, and we're familiar with a lot of the different functions that we can apply to them, like addition, subtraction, multiplication, division, all those sort of things. We're familiar with those since elementary school. As such, I think many of the ideas in number theory, or the things that we are trying to prove, are things that can be easily grasped by a layperson, someone who's not intimately familiar with deeper, higher level math. And as a result, I think that it can serve as a great starting point for your learning of higher level mathematics and diving deeper into higher level math and seeing how abstract concepts can arise from these simpler concepts and practice different proof techniques. It definitely sparked a passion in me. I remember in college I took a number theory class and loved it, and I feel like I learned so much about proof and numbers and really developed sort of a passion for math. Okay, so along with the natural numbers, number theory is also concerned with integers. We're going to talk a lot about integers. And integers are just an extension of the natural numbers that include some concepts that are abstracted from those natural numbers, like negative numbers and the concept of 0, which actually was not developed in a lot of cultures until after the counting numbers were developed. So the integers are all the natural numbers, the counting numbers, 0, and then all their negative equivalents. So we're also going to concern ourselves with the integers. Okay, and then additionally, over the course of this series, I'm going to use this textbook called Number Theory Through Inquiry by David C. Marshall, Edward Odell, and Michael Starbird. And this is the book that I used during college when I took a number theory course. And I think I really like this textbook because essentially, like, the way it works, they have a bunch of theorems and they don't write out the proofs. They have you go in, write out the proofs yourself, kind of discovering number theory through inquiry. You're discovering it by doing the proofs itself. You're kind of building up number theory on your own in a guided sort of way where it guides you through, like, this is like the natural progression of how these different theorems arise. This is how all these different concepts arise. And I found that in the class that I took, the way that the class was organized was we would go out, we would do these proofs on our own and come back to class, and then each of us would present different proofs. And then we'd all discuss them. The teacher would go through and explain like what's wrong with some of our attempted proofs that we did or what's good about them. And then we learned a lot just through doing all these different proofs. And I felt like I learned a lot. I gained a lot of mathematical maturity through this process. So if you want to get the most out of this number theory course, I would highly recommend that you purchase this book and go through the different theorems as I'm going through them. I think you'll gain a lot out of that. But okay, so next, let's jump into. So that now that we're done with the introduction into what number theory is, let's actually jump into a few concepts. And we're going to start with the concept of divisibility, which we actually briefly introduced in the introduction to proof techniques video. So this should be kind of a review for those of you who watched that, but we introduced it briefly, so I think we should go a little bit more in depth and kind of see the starting point of number theory as a starting point for number theory. And to start, let's start with a definition. So the definition of divisibility. And you also see this like it's a multiple of, or it's a factor of, it divides. Like you'll see a lot of different terminology, but we're going to describe this as divisibility first. Suppose A and B are integers. Then, oh, it says D in the book, so I'll use that just to have consistency with that. A and D are integers. Then D divides A, or is a factor of A, or you'll see different ways of saying the same thing, which we're going to denote as this. D divides A. That's what this symbol means here, this little vertical line denoted D divides A. If and only if there exists an integer k So if you remember this there exists symbol from that video, that's a quantifier that just says there exists some integer k such that A equals k times d. So this kind of formalizes the definition of divisibility. You'd also have learned this pretty early on in your mathematical career, likely, when you learn about, like, oh, what are the factors of A? Well, D is a factor of A. D divides A, basically. There's something that D can be multiplied by that gives you A. So let's see an example. As an example, 2 divides 6 because 2 times 3 equals 6. So 2 divides 6, 2 is a factor of 6, all that sort of thing. Additionally, 5 divides 70, because 5 times 14 equals 70. So there's some integer that you can multiply 5 by to get 70. However, 5 does not divide 26 because there's no integer there. So it's like, I think to get 26, it'd be 5 times 5.2 equals 26. But 5.2 is not an integer. So that's basically how divisibility works. And now to start, let's go through a few theorems about divisibility. So let's start theorem 1.1, the first theorem in this book. So we're going to let A, B, and C all be integers if A divides B and A divides C, then A divides B plus C. And for the proof, we're just going to use a direct approach, and most of the proofs today are going to be direct. There's going to be one inductive proof, and I think also a biconditional proof where we use a contrapositive proof in this video, but this one's just going to be a direct proof. So we're going to suppose A, B, C are all integers. A divides B and A divides C. So this is just that first premise in the proof, that P then Q. We're starting with P. We're supposing P. By the definition of divisibility, remember, if D divides A, then A equals K times D for some integer K. So in this case, A divides B. So this means by the definition of divisibility, B equals AX, where X is just some integer, and C equals AY for some X and Y that are integers also. So this just directly follows from the definition of divisibility. And now with these numbers, what can we do? Well, since what we're interested in here is whether A divides B plus C, let's just see what B plus C equals. Thus, B plus C equals AX plus AY, which means by the distributive property, we can factor out this A and just have X plus Y. And since the set of integers is closed under addition, so that basically means if you add two integers, the resulting sum is also an integer. So X plus Y is an integer. So since X plus Y is an integer, oh, I didn't mean to do that. Plus Y is an integer. Then we know that A divides B plus C. Does that make sense? This is because B plus C can be written as A times an integer. B plus C can be written as A times an integer, so A divides B plus C. Let's do another one. This one's going to be a pretty similar looking proof, but we're going to do it with subtraction. Just to kind of get the feel for how these sort of divisibility proofs work. Theorem 1.2 is let A, B, and C all be integers if A divides B and A divides C, then A divides b minus c. And this is going to be a very similar proof because these are very similar concepts. Subtraction is basically just adding a negative integer. But just for some more practice with these type of divisibility proofs, let's go over this as well. So we're going to similarly suppose that a, b, and c are all integers. A divides b, and a divides c. So, by the definition of divisibility again, b equals ax and c equals ay for some x, y in the set of all integers. Thus, what we're concerned about is the subtraction of these two numbers. We're concerned with the subtraction of b minus c. Thus, b minus c is equal to, just through substitution, we see b is ax minus c, which is ay. Similarly to before, we can distribute out this, or we can factor out this a, and we're left with a times x minus y. X minus y is still an integer because if you subtract two integers, you're still left with an integer. So, since x minus y is in the set of all integers, a divides b minus c, which is what we were trying to prove. So by direct proof, we have our result, and we've proved that theorem. Does that make sense? Okay, let's do one more proof with divisibility. This one is going to be a little bit different because here we're going to show multiplication. And this one is theorem 1.6. A lot of times it'll skip numbers. That's just because some of these are exercises, or I decided not to include them because the theorems are kind of redundant. But this theorem is let a, b, and c all be integers. So then the theorem is if a divides b, then a divides bc. And basically, you'll see the common theme of each of these is we're seeing how the functions of addition, subtraction, and multiplication affect the divisibility of certain numbers. So we can see that if it divides a, b, and c, it also divides their sum. If a divides b and c, it also divides their difference. Now we want to see if a divides one number, does it divide all numbers that are all numbers that have that number times some other integer, basically. All products that contain the number that it divides. So our proof, similarly to before, we're just going to use a direct proof. And the way we're going to do this is suppose a, b, and c are all integers, and let a divide b. So b equals ax for some integer x. Thus, bc equals, and we're just going to substitute in this ax for b, and this is typically how a lot of proofs go. You just start substituting stuff in. If you have a proof and you're trying to figure out how to get from point A to point B, look at what you're trying to prove and then start substituting the stuff. And typically you can kind of find some way to manipulate these things, manipulate the algebra a little bit to get you to your desired result. So we have BC equals AX times C. Just with a little bit of rearranging, we have A times X times C, because you can move these parentheses. That's just a property of multiplication. Thus BC. So BC is also the product of A and some integer. Integers are closed under multiplication. That means if you multiply two integers, you're still left with an integer. So xc is an integer. So bc is equal to a times some integer, and this means a divides bc. So we have our proof. Okay, so those are some very basic properties of divisibility, and you can kind of see how we use divisibility in a proof. Typically, when we see that something is divisible, we can break it out in terms of this definition where we have the number times the thing that divides it, or equals to the thing that divides it times some integer. And this integer is just any integer. We know it has to be some integer. We don't know specifically what integer. But using the fact that it is some integer, we can use that fact to make some sort of proof, or to write out some sort of algebraic equation, and from there we can get to our final conclusion that it divides something else. Okay, so with this, let's block this section off, and then we can get into congruence. Okay, so then for the next point, we're going to talk about the concept of congruence. And similarly to divisibility, we're going to start off congruence with a definition. And congruence is going to rely a bit on divisibility in its definition. So we're going to use these two concepts together in a lot of our proofs. So our definition for congruence, we're going to suppose that a, b, and n are all integers with n being greater than 0. So n is actually a natural number in this context, because n is greater than 0. It's a positive whole number, basically. It's a positive whole integer. So once we suppose this, we say that a and b are congruent modulo n if and only if, that's just what that IFF means. It means if and only if, n divides the difference of a and b. So n divides a minus b. And we denote this as a is congruent to b modulo n. And then we put this modulo n in parentheses just to kind of distinguish it from the relationship part, and we use three horizontal lines to denote congruence, as opposed to equality where we just use the two. And to start, let's kind of understand how we see this relationship in everyday life. So in the world of time, for example, let's say it is 11 o'clock. And we say we want to add 5 hours to it. Now, 11 plus 5 equals 16. But typically, unless we're in the military, we don't say 16 o'clock, generally in the English-speaking world. At least, especially in America, I know we definitely don't typically say 16 o'clock to people. Instead, we say 4. Here, let's actually just do it like this. Instead, we say 4 o'clock. And then we have the AM, PM stuff too, but yeah. So what we typically say, we'll say 4 o'clock instead. And the reason for this is because we express time in a modulo 12 world, basically. In other words, basically what happens is 4 is congruent to 16 mod 12. So expressing 16 o'clock and 4 o'clock is the same thing in this modular 12 world. The number line kind of works like a circle in this context, where we have obviously 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And once we get to 12, we just start over back at 1. So we're adding 1, 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 and then we get to 12, and instead of going to 13, we start the loop back over and go back to 1, because 13 is congruent to 1 mod 12. And this makes sense with our definition as well, because 16 minus 4 equals 12. And 12 obviously divides 12, because 12 times 1 is 12. 12 is a factor of 12, so this relationship works with our definition of congruence modulo n, or congruence modulo 12. So this is an example. Oof, wow. I should probably use the number pad instead of using my mouse on this. Additionally, for those of you who remember long division from elementary school, saying that something is congruent modulo n also implies that the two numbers have the same remainder when they're divided by the modulo n number. So in this sense, when 4 is divided by 12 in long division, it has remainder 4. When 16 is divided by 12, by 12, using long division, it also has remainder 4. And this sort of relationship continues. So 28 would also be congruent. And with that, let's go through a few examples. So the first example, let's look at the relationship of 45 and 9 mod 4. I don't need another parenthesis there. This is true because 45 minus 9 equals 36, and 4 times 9 is 36. So 4 divides 45 minus 9. So by the definition of congruence, 45 is congruent to 9 modulo 4. Let's look at another one. Is this true? Well, let's look at it. 37 minus 3 equals 34. But 5 does not divide 34. 5 is not a factor of 34. So as a result, this is not true. However, if we go to the negative realm and look at a negative integer, we can go 37 minus a negative 3, which is 40. And 5 times 8 equals 40. So 5 divides 37 minus negative 3. So in this case, the negation of 3, so negative 3, is actually congruent to 37 modulo 5. So one thing to note here is that just because the positive version is congruent to a number does not mean the negative version. Negative and positive number equivalents aren't always congruent to each other in the modulo world. Okay, so with all of this, let's discuss some properties of congruence. So we know with equality, there's a few properties of equality that hold. And we're going to compare congruence to equality. So we have the reflexive property. A equals A. We also have the symmetric property. I think I need a second M here. Actually, I'm not sure. I don't know how to spell apparently. Symmetric, A equals B. So, okay. Symmetric means that if A equals B, then B equals A. And then finally we have transitive. If A equals B and B equals C, then A equals C. And these are just some facts about equality specifically. But do these properties, and these properties basically make equality what's called a equivalence relationship. That's kind of beyond the scope of this particular video, but we might get into it later in this series. We'll see where we get. It's more of a concept in like abstract algebra, but yeah, so basically this is an equivalence relationship, but we want to see now how these properties kind of apply to the congruence relationship. Is A congruent to A mod n? If A is congruent to B mod n, is B congruent to A mod n? If A is congruent to B mod n and B is congruent to C mod n, is A congruent to C mod n? Now the answers to these, instead of just taking them for granted, we're going to go through and prove them one by one. So let's start with the the reflexivity of congruence. Let A and n be integers with n greater than 0, then A is congruent to A mod n. So for our proof, we're going to go through and say let A and n be integers. We're just going to prove this directly with n greater than 0. So this is our starting point, and we want to get to the fact that A is congruent to A mod n. So remember that what we're trying to show is that n divides A minus A, basically. So what is A minus A? A minus A equals 0. And we also know that n times 0 equals 0. And 0 is an integer. So A minus A equals n times 0, which implies n equals, which implies that n divides A minus A, hence A is congruent to A mod n. So we know that the congruence relationship is reflexive. The congruence relation is reflexive. And then next we're going to go over whether it's symmetric. 1.10. And this numbering system, we're going to use this a lot more later when we're referencing back to older theorems. So for 110, we're going to let A, B, C all be integers. And then maybe I'll pull this out a little bit. With n greater than 0. If A is congruent to B, mod, oh, I meant to do a n here. To B mod n, then B is congruent to A mod n. So for our proof, similar to last time, we're just going to start by starting out with let A, B, and n all be integers with n greater than 0, and let A be congruent to B mod n. And this means A divides, or here, let's do it like this. I want to use so in that sentence too. So thus, n divides A minus B, so A minus B equals nk for some integer k. So this means B minus A, which is what we're concerned with when we're proving equivalence, because we want to show that B is congruent to A mod n, not that A is congruent to B mod n. So we want to flip this, and this is equal to negative n times k, because all we're doing is flipping. We're adding a negative to both sides, basically, which means that it is congruent to n times negative k. And negative k is still an integer, so this means since negative k is an integer, n divides B minus A. Hence, B is congruent to A mod n. So this proves basically that the equivalence relation is symmetric, similar to equality. And then finally, we're going to go over the last theorem, which is transitivity. And this is going to be let A, B, C, and n be integers with n is greater than 0 if A is congruent to B mod n and B is congruent to C mod n. Then A is congruent to C mod n. And for our proof of this, we're going to start just with the first part. So this is let A, B, C, and n be integers with n greater than 0. And we're going to start with, and let A be congruent to B mod n and B be congruent to C mod n. And this, from here, we have, by the definition of congruence, then A minus B. We know that n divides A minus B from this part, from the fact that A is congruent to B mod n. So this means that A minus B is equal to nx for some integer x, and B minus C from this is equal to n times some integer, and we'll call that integer y, for some x, y in the set of all integers. So we know that nx plus ny equals A minus B plus B minus C. And these two B's cancel out, so we have that A minus C is equal to nx plus ny. Hence, and I'm starting to run out of room here, but I started it anyways. Hence, A minus C equals n times xy, x plus y. So, since x plus y is an integer, n divides A minus C. Thus, A is congruent to C mod n. And that is our proof. So we have reflexivity, we have symmetricity. I don't know if that's a word. I don't know what the right word for that is. But we have that the equivalence relationship is reflexive, symmetric, and transitive, which means similar to equality, this is an equivalence relationship. However, as we'll get into, there are also some key differences between congruence and equality that we can get into in the rest of this video. So we're going to start by showing that certain properties hold for congruence. So, with equality, we know that if A equals C, or A equals B, and C equals D, then A plus B equals C plus D. But does this hold for congruence? Well, let's look at theorem 1.12. And this theorem is let A, B, C, D, and N all be integers with N is greater than 0. So we're going to say if A is congruent to B mod N and C is congruent to D mod N, then A plus C is congruent to B plus D mod N. And the way to prove this, similar to before, we're going to start with let A, B, C, D, and N all be integers with N greater than 0. And we're also going to let A be congruent to B mod N and C be congruent to D mod N. And as a result, we know that thus A minus B equals N times X and C minus D equals N times Y for some X and Y that are integers. And based on this, what else do we know? We know that Nx plus Ny equals A plus C, or sorry, let's do it like this. Let's do it more slowly. A minus B plus C minus D. And doing some rearranging, we can get this to look like A plus C minus B minus D, which equals a plus c minus b plus d. Then a plus c minus b plus d equals n x plus y. So what we know from there is basically that n divides a plus c minus b plus d. And because of that, hence a plus c is congruent to b plus d mod n. And that's what we were looking for, so the proof is complete. So we can see that basically congruence, if you add two congruent numbers together, you also get a congruent number. So that will be that theorem. And next, let's look at what happens if we do the same thing, but we do it with subtraction. And we know this is true in the case of equality because a minus b, or, oh my gosh, this is wrong. Equals b plus d. Sorry, that was a mistake. Okay. Then a minus c I'll note that in the comments. A minus c equals b minus d. This is a fact of equality, so let's look at how this works for subtraction. And this theorem is going to be theorem 1.13, and it's very similar. It's going to be very similar to the last one. We're going to let a, b, c, d, and n be integers with n greater than 0. And then if a is congruent to b mod n and c is congruent to d mod n, then a minus c is congruent to b minus d mod n. And for our proof, we're going to do very similar to before. This proof is going to be almost identical to the last one, but it helps us understand how sort of these modular functions work and how the definition functions in the context of a proof. So we're going to let a, b, c, d, and n all be integers with n greater than 0. And then we're also going to let a be congruent to b mod n and c be congruent to d mod n. And because of this, we know that a minus b is nx equals n times some integer, and c minus d equals n times some integer for some so because of this, we can take nx minus ny this time, which if you remember last time we just took nx plus ny, and based on that we will have a minus b minus c minus d, and with that that becomes A minus C minus B plus D, and this is equal to A minus C minus B minus D. And based on all this, what we're going to get from this is thus A minus C minus B minus D is equal to nx minus y. So this difference between these two is equal to n times some integer. Hence, A minus C is congruent to B minus D mod n, which ultimately is what we were trying to prove. So great, okay. We have shown that theorem to be true, so now let's move on to the next theorem. And I'm running out of space over here. To expand the page, I just want to put all these at like the same kind of point on this. Maybe I'll extend this one a little bit longer. Okay, so we also know that if A equals B and B equals, or not that, and C equals D, then A times C equals B times D. But does this hold for congruence? Well, let's look at this next theorem. And in this case, we're going to let A, B, C, D. Oh wait, this is theorem 114. And n all be integers with n greater than 0 if A is congruent to B mod n and C is congruent to D mod n, then AC is congruent to BD mod n. And this proof is a little bit trickier, but I think that the technique that's used here is interesting and will be helpful for you in your proofs down the line. So the proof of this one, we're going to start by supposing that A, B, C, D, and N are all integers with n greater than 0. We're also going to assume and let A be congruent to B mod n and C be congruent to D mod n. So we have this all lined up, and then with this, what we're going to look at is, well, we're going to start by basically showing, we're going to start by just drawing out the basic consequence of congruence by the definition like we have done in the past couple. So A minus B equals nx, and C minus D equals ny for some x and y that are integers. Thus, AC minus BD, which is ultimately what we're looking at, because what we're trying to prove here is that AC and BD are congruent mod n, which would mean that AC minus BD, which is this thing right here, would have to be divisible by n. But looking at this, what can we do about this right here? Well, notice that this has a C and this has a B, and those could be factored out. Now this one, I didn't come up with this technique. I think I remember someone showing me how to specifically solve this proof. But once you see it, it makes a lot of sense. And doing techniques like this can be really helpful in proofs. And this is where some of the creativity of proving things comes in. So what we're going to do here is take AC, and then we're going to subtract BC and add BC. So this is ultimately comes out to 0. So these two are equal because this comes out to 0, and AC plus 0 minus BD is the same as AC minus BD. So adding and subtracting the same term can be really useful in proofs, and we'll see why in a second. So what we're going to see is this term, the C term, can be factored out. And we'll also see that this B term can be factored out. Okay, why is this helpful? Well, notice that this A minus B and the C minus D are the terms that we've come up with some equivalent form of that contains n. So what we have here is C times nx plus B times ny. And now both of these terms contain an n. So what we can do is factor out the n, and we're left with n times cx plus by. And cx plus by is an integer. So what we have here is n times some integer equals AC minus BD. So we know that n divides AC minus BD. So let's just write that out. And now, based on this, we have basically what we need. By the definition of congruence, AC is equivalent to BD. And that's our proof. So a key takeaway from this proof is that sometimes when you're stuck, adding and subtracting a term can be helpful, but it's not always the easiest to figure out what specifically to add and subtract. But with all this, we've shown that these three ideas are true. Now, let's think about the concept of division. So if we have that A C equals BC, and C isn't 0, because you can't divide by 0, we know that A equals B. But this is going to be our first difference between congruence and equality that we're going to find here. But this is not true for congruence. If we have AC AC equals BC and C and C does not equal 0 mod n. It's not always true. That A is congruent to B mod n. And to see why, let's see a counterexample. Let's consider the numbers 2 and 8. So 2 is congruent to 8 mod 6. Because 8 minus 2 equals 6, but 6 times 1 is 6. Okay, so 1 times 2 is congruent to 4 times 2 mod 6. However, 1 is not congruent to 4 mod 6. Because 4 minus 1 is just 3. And 6 does not divide 3. There's no integer you can multiply 6 by to get 3. You'd have to multiply it by 0.5, which isn't an integer. So basically the point here is that this relationship that holds for equality does not hold for the mod world, for the modular world, modular arithmetic world. And the important thing here, this is why we have to go through and prove all of these different things, because just because something feels intuitively true because it's true for something we understand like equality doesn't mean that it's true in this different modular world. So that's kind of why we go through and prove all of these different things. In math, it's commonly the case that something that we might see as intuitive isn't necessarily true. And that's why proof is so important. It's so hard to make a generalization from just the things that we observe until we go through and prove them. Okay. Up next, we're going to show another proof for modular arithmetic. In this case, the theorem is 1.18. And we're going to let A, B, K, and N. And this is going to be an inductive proof, actually. So this one should be interesting. We're going to let A, B, and N all be integers with K, N greater than 0. And our statement is going to be if A is equivalent to B mod, or congruent to B mod N, then A to the K is congruent to B to the K mod N. Now, if you don't remember proof by mathematical induction, I would encourage you to go back to my proof introduction to proof video, and we can look over that again just to refresh yourself. But the proof here, we're going to go through and prove. Well, we're going to start basically by supposing A, B, K, and N are all integers with K and N greater than 0, and A is congruent to B mod N. And what we want to do is go through and show that this statement, which we're going to denote as SK, A to the K is congruent to B to the K mod N. We're going to show this statement for every value of K greater than 0. And we're going to do this through mathematical induction. So we're going to start with the base step. And the base step is going to be S1. And we're going to say, we know that S1 is true because A1 is congruent to B1 mod N is equivalent to A is congruent to B mod N, which we suppose to be true. So because we already know that this is true, we know that our base case is true, basically. And then in the next step, we're going to go through and figure out if we can. We're going to basically let this is the inductive step. Let K be greater than or equal to 1, and we have to say greater than or equal to 1 because we have to start at this rung of 1, and suppose SK is true. So a to the k is congruent to b to the k, b to the k mod n. And what we need to do is show from this that sk plus 1 is true. We need to show that sk implies that sk plus 1 is true. This is like climbing up to that next rung of the ladder, basically, if you remember from my other video when I explained how mathematical induction works. Hence, oh wait, no. So this is going to be the first time I think that we cite another theorem in a proof. And the theorem that we're going to use is theorem 1.14. And AK times A is congruent to BK times B. And we know this because, let me add a period. And we know this because we know that AK is congruent to BK mod n. And we know that A is congruent to B mod n. And remember, the product of two congruent numbers are also congruent. And that's by theorem 1.14, which we proved over here. It's this theorem. So basically, imagine substituting A congruent with B mod n, and A to the K is congruent to B to the K mod n. So we know that the product of the two are going to be congruent. So going back to our current proof that we're working on, we know by theorem 1.14 that A to the K times A is congruent to B to the K times B mod n. And this means that A to the K plus 1, because A to the K times A is equal to A to the K plus 1, is congruent to B to the K plus 1 mod n. And just to kind of spell out this logic a little bit more, hence sk implies sk plus 1. So the proposition is true. By mathematical induction. So basically, we proved that the first rung of the ladder is true. We proved that S1 is true, and then we proved that once we're on a rung, once we have some sk for k greater than or equal to 1, so S1 for example, we can get to the next rung, kx plus 1 basically. Sk always implies sk plus 1. Okay, so with this we can actually prove a result that you might know practically from maybe your elementary school math days when you're thinking of factors. And this will be the final theorem that we prove in this video. We can prove the divisibility trick for threes. For example, you may remember that 27, for example, we know that 3 divides 27. We also know 2 plus 7 is 9. And 3 divides 9. And because of this, there's this trick that you might have learned where to see if a number is divisible by 3, you check if the sum of its digits is also divisible by 3, or if 3 is a factor of the sum of its digits. So for another example, like 33. 3 plus 3 equals 6, and 3 divides 6, so we know that 3 divides 33. Additionally, if we want to make this a little bit more complicated, we could take the number 717 and 231. Well, 7 plus 1 plus 7 plus 2 plus 3 plus 1 equals 21. and 3 divides 21. So we know that 3 divides 717231. And just to kind of verify this, let's just take out the calculator quick. So we're going to take 717231 divided by 3. And we can see it's an integer, so 3 does divide this. So this trick seems to work, but let's prove it. So our theorem is going to be written kind of out in words. And this is theorem 1.21. So the theorem is this. A natural number that is expressed in base 10. Base 10 is just the numbering system we use. This is where we get the digits that we use from. If and only if the sum of its digits is divisible by 3. So how do we even go about proving this? We don't have a clear congruence relationship here. We see divisibility here, but we're not working with like A's and B's like before. So to understand how we can do this, let's actually start writing things out and kind of see where we can get something that we can work with. So we're just going to start by letting n be a natural number. And because of that, we can write out the natural number as kind of a decomposition of its numbers. So a0 plus 10 to the 1 a1 plus ... plus 10 to the k minus 1 a k minus 1 plus 10 to the k a to the k. And this is basically assuming that we're writing n out as a k minus 1 ... a1 a0. This is not multiplication in this case. These are like the actual digits. So like it could be 9 7 ... 3 2. So like ak would be 9, ak minus 1 would be 7, a1 would be 3, a0 would be 2. This isn't multiplication, that's actually how the number would look. So say we had n equals 1374, a to the 3 is 1, a to the 2, a2 is 3, a1 is 7, and then a0 is 4. Does that make sense? I hope so. And because of this, the way that this is also written out, we can also express this in terms of like 1,000 times 1, 3 times 100, 7 times 10, and 4. So that's kind of what we're doing here. We're taking a0, and then we're adding 10 times the first digit, and we're adding 100 times the second digit, and 1,000 times the third digit, all the way up to however many digits there are. So that's kind of how we're breaking this down. So with this, the next thing that we can do, the next thing that we can note is that 1 is congruent to 10 mod 3, since 10 minus 1 is equals to 9, and 3 divides 9, because 3 times 3 is 9. So we have 10 is congruent to 1 mod 3. So by the theorem that we just proved, theorem 1.18, 1 to the k is congruent to 10 to the k mod 3. And 1 to the k always just equals 1. Like, no matter how many times you multiply 1 by itself, you're always going to be left with 1. 1 times 1 is 1. 1 times 1 times 1 is 1. Times 1 is 1 again. Like, it keeps going. There's going to be so many 1s. But it's always going to end up being 1. So we have this. We have n equals a0, or let's write it out like this. So what we find out here is that a0 plus 10 to the 1 a1 plus dot dot dot, and we'll actually write out here for some, just to be like consistent, or just to have good notation practices. We're saying that all these are integers. All these a's are integers. Plus 10 to the k minus 1, a to the k minus 1, plus 10 to the k, ak, is congruent to a0 plus 1 to the 1, a1, plus 1 to the k minus 1, ak minus 1, plus 10 to the k, or not 10 to the k, we'll say 1 to the k because they're congruent. 1 to the k, ak, mod 3. So what this basically means is that n is congruent to a0 plus a1 plus dot 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 plus ak minus 1 plus ak mod 3. So this proof kind of gets us a starting point actually to our proof, and this direct implication of this is this if and only if statement. But to kind of spell this out more cleanly, let's write this out. Let's go through and see how this logic kind of works itself out, to see how this direct implication works. So the first thing that we're going to do is prove this direction, and we're going to prove this directly. So we're going to assume the natural number that is expressed in base 10 is divisible by 3. And we want to show that that means that the sum of its digits is divisible by 3. So we're going to start by supposing n is divisible, or suppose 3 divides n. So n is divisible by 3. Those are equivalent statements. So in other words, 3 divides n minus 0. Thus, n is congruent to 0 mod 3. Now, by the transitive property, which we learned previously, I think this is theorem 1.11, because we know that n is congruent to the sum of its digits, mod 3, we also know that a0 plus a1 plus dot 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 plus ak is congruent to 0 mod 3. So 3 divides this sum well, if we just subtract a 0, that's the same as just not subtracting anything at all. And this means 3 divides the sum of the digits of n. Now, so that shows that direction. Now let's prove the other direction. And we're going to prove this by the contrapositive. So we're going to suppose that the then part, so we're basically the inverse of the statement is that if the sum of the digits is divisible by 3, then the number is divisible by 3. So just do the contrapositive, we're going to suppose that the number is not divisible by 3 and show that the sum of the digits is also not divisible by 3. So 3 does not divide n minus 0. And this is going to be a very similar looking proof. Thus, n is not equivalent to 0 mod 3. So by theorem 1.11, a0 plus a1 plus dot 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 plus ak is not congruent to 0 mod 3. So 3 does not divide a0 plus a1 plus dot 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 plus ak minus 0. So 3 does not divide the sum of the digits of n. So, in other words, we have proved both directions of this if and only if statement. So you can go ahead and freely use this little divisibility trick for 3, because if the sum of the digits is divisible by 3, then the number is divisible by 3. If the number is divisible by 3, then the sum of its digits is always divisible by 3. So this trick works perfectly at determining whether or not a number is divisible by 3. Okay, so that's it for this video. That's all I wanted to go over today. And if you enjoyed this video and want to keep seeing more, please please subscribe if you want to be notified. Please join my Discord if you have any questions, want to talk about stuff. If you enjoyed this content or my philosophy content, join the Discord. And if you really enjoy this math content, please support me on Patreon, and it'll give me the motivation to keep posting these videos and keep up these weekly uploads. And with that, thank you all for watching, and I hope to see you all in the next video. Peace.